So quick show of hands, who here flew in for DevDay? Everyone fly in? Yeah, me too. Turns out that flight you took could have not happened if it wasn't for systems like we're going to talk about today. And so as you see, these are real headlines that you see. There were actually hundreds of flights grounded because of fake parts for our airplane, allegedly. And yes, there's also an eBay listing for a Boeing 737 emergency exit door. Now, can you imagine if this is what you saw on your flight the other day? And the description is pretty funny. It says, used with a small ding, fell on the ground, no big deal. But in a serious question, how do we prove that parts that airlines, automobile companies, buildings are getting are actually proven and to be real and coming from the manufacturer? How does an aviation authority verify that the serial number on that door traces back to the actual manufacturing process? So we'll dive into that today. So my name is Ajaz Merchant. Welcome you guys to Designing for Scale workshop. We'll try to do a batching 1,000 records on chain, and you'll all join that with me as well. So this will be a hands-on workshop. So we'll go through some concept first and then go into the actual running it yourselves. Sounds good? Let's start. So the agenda quickly is that we'll talk about Merkle trees. We'll cover the concepts, who's already using these in the real space right now in the world, and why does this actually matter? And then we'll go through the workshop together, get our hands dirty with HCS, which is Hedera Consensus Service. We'll batch records, we'll anchor them on chain and verify them all together. And then at the end, we'll do a Q&A if needed. And if there is some bonus time remaining, I'll go through a way to run the network locally for you. So those who are interested, please stay at the end. And then if you have questions, we'll wait till the Q&A, but I'm excited to go down this with you guys. So before we begin, let's talk about what does it mean to actually batch 1,000 records on chain? Why would you even need to do this? And if you take back to our airplane example, just put your shoes in an aeronautical engineering firm. You manufacture a part that could be a door, that could be those engine parts, the cockpit parts, that could be the wheel itself. But you want to stamp it, want to prove that it's yours, and then when you ship it to Boeing or SpaceX or whoever it may be, every part of that life cycle is generating an event. You have your quality checks, your manufacturing itself, you have shipping, delivery, installation, and that's all for just one part. Now take a step back, and that could be 20 to 50 events just for one part. You add in the entire component of that plane, you're talking about thousands of parts. Now you have a really large data set here. So you want that tracked, you want it to be provable, and you also want a regulatory authority to actually be able to check it themselves. But when you think about submitting all of those transactions on chain, that becomes pretty expensive. And I think the best way of going about that is Merkle trees. So before we begin getting to that, does anyone know what a Merkle tree is? Show of hands. A few people? Great. So essentially, a Merkle tree is a hash of hashes. You start with your data. At the bottom here, you start with your data. You hash it, and you keep combining these hashes into pairs until you end up with one root. That's your single root hash. And that single root hash is, imagine, your single source of truth. So through this diagram here, you have your data. That could be anything, JSON objects, that could be transaction records, that could be airplane manufacturing parts, sensor readings, anything that you need to track, that is your data. And then each piece is hashed via SHA-256, and those hashes then become your Merkle leaves. And then moving above that, you'll hash each of those hashes. So hash 1, 2 becomes hash 12. Hashes 3 and hashes 4 become hash 3, 4. And those become your Merkle branches. And as you can see, you work your way up to the root. And then those two hashes together, hash 12 and hash 34, then are hashed again to become hash 1234. That is your Merkle root. And that is the one single 32-byte hash that represents all 4 pieces of data. Now you can imagine when there's more data, you have a few more hashes, but the end goal is the same, to get one Merkle root. And there's also one key insight, is that if anything is changed within that data, that root will completely change, and the fingerprint of this entire batch lives on that Merkle root hash. Sounds good? And just want to go through some current use cases that are out there. You see GitHub, and now GitHub is using Merkle trees for every commit. Every commit on Git is a hash that represents its parent, and that enables in integrity checking and syncing. Microsoft SQL Server uses Merkle trees for ledger tables. And the bigger one that we want to showcase today is Google Trillion. Now, Google Trillion is a open source library for transparent and cryptographically verifiable data stores on Google. As you can see, it's got about 4,000 stars, about 420 forks, and almost 1,000 projects are using this right now. And teams like Apple, Google, Cloudflare, DigiCert, and Let's Encrypt are all using this from Google Trillion. And the best thing about this is that these projects here are using this as a certificate transparency log. So every time let's say Let's Encrypt is issuing an SSL certificate, that is going into a Merkle tree. And this is kind of how you see almost the internet certificate authority kind of being honest. So when we talk about Merkle trees for supply chains, for financial auditing, we're building on a battle-tested infrastructure that the biggest tech companies in the world already rely on. And so we've already discussed a little bit about the properties of a Merkle tree, but essentially they have a binary tree of hashes. The leaves are hashes of individual records. Those branches that you saw are a hash of children concatenated together. And that single 32-byte root is representing the entire batch. But what I'd like to showcase here is this table. And I'm sure that your eyes are already gluing to what happens with the pricing between without batching and with batching. So as you can see, the last one, 100,000 records, without batching would cost $80 on HCS. Now, with batching, just like 10 records of 10, 100, 1,000, 10,000, and even 100,000 all costs less than a tenth of a cent. That's absolutely incredible. Your savings is to the right by 6 decimals. That's kind of bonkers, if you ask me. And this proof size grows logarithmically. So that's cost is staying flat. So that's the entire point here. And you're kind of curious, hey, how does Hedera fit into all of this? Well, Hedera has the HCS consensus service on Hedera. It's essentially a public and immutable log, messaging log, that when you create a topic, you can then submit messages to it. That's it. It's simply is that. It's powerful because not only does it give you a message log, but it has native performance for about 10,000 TPS. You can amplify your trust with validating data in multi-party databases, notary services, or anything that needs transparency with shared infrastructure. There's guaranteed order. You can get fair total consensus order there with accurate timestamps, a running hash of the topic, and plus a state proof that guarantees correctness. And then obviously we have the ecosystem integrations, things like the Hyperledger Fabric. And at the bottom you see there's a little flow. I think that flow is absolute key to what HCS actually is. You create a topic, you send messages to that topic, those messages get processed with consensus there, and that's exactly what HCS is, and then anyone can audit it, and that's the best part. And I love this quote by Brian Gross from IBM Blockchain, simply putting, Hedera is making a meaningful contribution to furthering the capabilities of distributed networks by exposing this capability. So we'll move forward here to the demo here. So if you guys want to follow along, there's a GitHub repo here for the best workshop, because this is your best workshop for the day. So I'll give you guys a second if you guys want to try that out. And then once we have everyone taking care of that, we'll give it a go. Beautiful. Awesome, thank you so much. And then, so I'll go through the setup and the scripts that you'll go through, and then I'll go through at the end so you can see what it looks like. But once you get to that repo, you can then clone the repo as you would, cd into the directory, and then run npm install. Then you can just copy the environmental examples and put in your own. And once you have all that taken care of, we can then get your credentials at portal.hedera.com. If you don't have an account, please make an account, and then you'll show your ID and your key. So the ID you can copy paste over to your env file that you just copied over, and paste it into the 0.0.xx part for your ID, and your operator key will be under more details, so just get that 302 private key, copy that over, and paste it in there. The topic ID will leave blank for now, and then we'll get that in just a moment, and the network should be the test nets as you see there. Beautiful. So the first script we'll run is the create topic. This essentially is creating your own personal topic, your own message. And once it's created, anyone can read this message or any messages on this topic. And then when you submit a message, you are then paying for that message from your account. When this runs successfully, you'll see the output there, as we have there, a green check mark with your ID, the Hashscan link. And we'll go through this all in just a moment, but just showing you what it looks like, giving you a little bit of knowledge before you run it, so you know what you're doing, you know what you're getting yourself into. The next script is you're going to compute the Merkle root here. By default, this uses a batch of 10, but if you're brave enough on your computer, you can actually update this with a dataset batch -100 or 1,000. You can go more than that, but those two we recommend for the first go through of this demo of this tutorial. And then what's happening under the hood, it's first loading that record that we have from the file, and then each record is a payment transaction that has an ID, a timestamp, a type, and a payload, which is all very important. Two, the second step is it canonicalizes each record, and that's just a way of saying that the JSON keys will be laid out deterministically, only because when you have a record, if it's changed around from the record, it'll have a different hash key. So it's all done in the same way, canonicalized. So it always has the same one. So A1 in B2 may not be the same hash as B2 and A1. So it's ordered correctly. So that always happens the same hash. So all these are hashed, obviously, with SHA-256. And then now we're starting to create that leaf, that hash. So you have the Merkle tree being built up from the bottom. Then we'll hash those bottom ones together. We'll pair those again, and we'll keep hashing it until we get to that Merkle root. And then you should see that root hash in the terminal, as I have down there. It's that 64 hex character. It's about 32 bytes. Whether you have 10 records or 1,000, that root is always going to be the same size, and that's the entire magic that we're going to show off today. So the next one is the third script, which is the anchoring root on HCS. This is where we can now put this on chain. What this script does, it recomputes the root locally on your computer, and that's more of a check for integrity. Then it wraps that into a structured JSON root, as you see there. So you have your schema, your Merkle root, your record count, whether it's 10 or 100, using the hash SHA-256, and then it'll also confirm with the batch JSON that you have. And once you have that, you'll get a transaction ID and Hashscan link once you run that script. And then we'll show what that looks like in just a moment. And then there you should have a 260-ish byte message representing all of the proof of all those 10 records, 100 records, whatever it may be, or 1,000, or even 100,000. And all that is cost of less than 1/10 of a cent. Now that it's on chain and now it's timestamped with consensus time, it can never be changed, and it's there for the world to see. So that's exactly what we're trying to go for. And when you do this, before going to the next step, you want to maybe wait 5-10 seconds so the mirror node can then take in that information and index that message. So the next two scripts are going to be verifying the batch and then verifying a single record. So the first one is verifying the batch. So you'll run this script for verify batch.js. And what's happening here is that it's recomputing the Merkle root locally with that JSON file. Kind of the same pipeline as before. We have the canonicalization of it, the hashing, and the building of the tree. And then is now querying the mirror node, which is a free public API. There's no auth required. There's no smart contracts. There's no tokens needed. And it's all fetching the latest message from the topic that you've submitted to the HCS. It parses that anchor message. And then what it does is it's pulling the Merkle root that's stored on chain. And now this is the cool part. It's comparing the local root that you have on your computer versus that on chain root. And once you get that, you'll have at the bottom right you have a green check mark passing that, yes, these two are working together. They're the same thing. And the best part about this is that anyone can verify this. Anyone, anywhere. The mirror node is free and public. You don't need to trust the person who did this. You don't need to trust the special. You don't need to get special keys. You don't need any special permission. The Hedera network is that source of truth. And the part that might be crazy is that if any one particular batch has been tampered with, one byte, this check mark will not be there. So you know something has been tampered with, something is going wrong. And I think that is the most key part of this whole situation here. And then going back to our airplane example, right? This is how we can prove that that door isn't from an eBay listing, but actually from a manufacturing firm. So you check that serial number on that door against the Merkle root here on HCS, and if it matches, it's real. If it does not match, something's been tampered with, and you can then check without going to find the manufacturer. You can understand what's happening here, and Hedera offers this service to you for free. And then last thing we'll do here is we can kind of check on one single record here. So you can run the script, and it's defaultly going to batch 10 in the 5th record of this 10 record. Maybe you don't want to download all 10 records or 1,000 records. So this way you can only just check one record to make sure that you can get to it and check it. Maybe the other records are maybe confidential, so you don't have access to them. So this is helping you get that one record and checking it against on-chain. So here we'll use actually a Merkle proof. And a Merkle proof is just a path of sibling hashes from your leaf up to the root. So for a batch of 10, that's only about 4 hashes. For 100 records, that could be 7 hashes. For 1,000, it's about 10. And so the verification works is that you start with your record's leaf hash. Then for each step in the proof, for all 4, you have a sibling hash in its position, left or right. And if the sibling on the right is yours, you hash that one first, then the sibling. And the opposite, if it's on the left, sibling first, then yourself. So you're always having a pair partner here to route all the way to what is anchored on HCS. If you have a scavenger hunt, feel free to add that in now. Beautiful. And so what we'll do is I will showcase the code real quick and show you how that works. So just give me just a quick second. So yes, so here now I have the first record. What I did was I've already added this topic to my env file. Let me make this a bit bigger. That could be better. So I've done the first one, as you can see, and it gave me a topic, which I've added to my ID. We'll then run the second compute route. I have it as batch 100. So as you can see, it's loaded 1,000 records. It's canonicalized and computes those leaf hashes, and now I have this route that has my entire records all in one place. Then we'll go and do the third one, which is the submitting the anchor. And once this is built, you can kind of see here that I'll get the Hashscan link, so we can kind of go that right now. And it looks just like this. And I can go to messages, and I can see that my message is now here on HCS. Beautiful. And then we'll verify the batch together as well. And you can see both that the mirror node that I have is matching my local data set. My ID is confirmed there as well. And then I'm interested in just doing one batch for a single record. This one's saying data 10, but I think that's okay. I think it's just because it's defaulted that way. But even if that's the case, it's still checking that the root locally for that one single hash is now matched to the one on chain. So just to kind of go back to what we were talking about, just one second. So we've kind of learned 5 things here. That the first is the cost problem. When you're trying to store individual records on chain, it does not scale. So we want to get 100,000 messages on HCS without batching would cost $80. With batching, less than 1/10 of a cent. To do this, we'll use Merkle trees to enable this batch verification. You can kind of hash everything down to a single root, and the proof sizes are growing logarithmically. And then HCS is the perfect anchoring layer. It's public, immutable. It's a message log with consensus timestamps. Low cost, high trust, very ideal here. The fourth one is now you can verify entire batches and single records cryptographically without downloading the entire batch, which is great for storing data and not storing excess data. And fifth thing is that we learned is that the mirror node is free and public, so we can then verify with no keys, no permissions, just having the trust required from the network. So yeah, and then I think we have a little bit more time, so we'll kind of discuss a way to run the network on your own computer. But before we go into that, any questions that we have? Fantastic. So I want to talk about Solo. So this Solo is a wonderful tool. I've been using it. A lot of people have been using it as well. This is a way to kind of test projects without having to get testnet tokens. It's a CLI tool, and so this repo you can get access to. I would suggest you guys going through this in your own time. It takes some time to set up, but it's actually fantastic. It's a CLI tool that can run a consensus node, a mirror node, a JSON RPC relay, all inside a local Kubernetes cluster. It is fantastic. I love messing with it, and people have been getting a lot of fun out of it. And so just a quick idea of how to install it. If you have these requirements, Node.js to 22, Docker desktop, and you have Mac OS, Linux, or Windows, and you have a 12 gigabyte RAM, 6 CPU cores, all that's what you need to kind of get it started running on your laptop or devices. I suggest you try it out. And then the instructions to install it are on the repo, but essentially you're just going to set some you'll set some environmental variables. Once you have that, that'll take the longest time. Once you run it and deploy a network, that could take about 10 to 15 minutes or so. So just be mindful of that. And then you can do a quick prompt to verify the deployment, and it'll probably look something like that on the right side there. So we'll have this out for you guys if you're interested. And then the setup is pretty easy. You can then run this same demo that we saw here, and then just change the network configuration on your ENV to Solo, and then run this same setup, the same 5 scripts, and then you can do this on Solo, and you'll see that you can run the entire network from your own laptop, and I think it's magical. So you can then run these whenever you get a chance, and run those 5 scripts again. And this is a quick recap of what we did today so far. That's a wrap, actually. So thank you all for being here. I appreciate you guys' time. I'll also be around. If you have questions about Solo for HCS, I'll be around, so give me a shout. And thank you for your time, and enjoy the rest of that day.